on the BC Calculus exam, there are only 2 advanced integration techniques that you have to know. If you look at your textbook, there are actually 4 integration techniques that we will end up learning, but before the AP test, I'm going to focus on just the ones that are on the AP test. We learned before the integration by partial fractions, by doing fraction decomposition. So that was called, again, integration by partial fractions. This is called integration by parts. So you can see that the names kind of get annoying to remember which is which. Now, I'm going to first just show you where the formula comes from quickly. If you don't know where the formula comes from, you're still good to go, but you should know where formulas come from. You know the product rule of derivatives. If 2 functions are multiplying and you take the derivative, it's keep the first multiply by the derivative of the second, plus keep the second multiply by the derivative of the first, in whichever order you want. If you take that formula and integrate, if you integrate the derivative of f times g, that's going to be f times g, but they switched sides. I did a photocopy or a screenshot from the textbook. Then what was on the right side is now switched over to the left, but that is now the integrand of an integral. So both sides got integrated. From there, if I isolate one of these 2 over the addition, so I'm isolating this one, we get a formula. Now that formula looks a little bit annoying to read, so what we do is we shortcut the formula into U's and V's to produce the formula that people memorize, which is, and watch me on this, are you ready? Are you ready watching the screen? Ultraviolet voodoo. That's how people remember it. However, you don't have to memorize it that way. It's just a nice little memorization technique that you can choose to use. Now, I want to point out to you how that formula is the same as this one, because it will also help you to understand the way that we use this formula. And that starts with saying, understand that u is an entire function with respect to the x variable. And v is an entire function with respect to the x variable also. If I find du dx, that's the same thing as saying find f prime. But when I isolate the differential du, I can see that if u is an entire function with respect to x, du is an entire derivative function multiplied by the differential dx. So what I'm going to do is I'm going to point out to you where you see f prime of x times dx, we write just du to simplify matters. And then if we decide that v will represent g of x, then we just say, oops, I wrote the wrong letter, v, trying to make it a very sharp v and a tail on the u to almost make it look like a w to not get it mixed up. Okay. Then you can see here that you have u times v. But when we're looking at the integral that we begin with, you want to realize that you have to break it up into two things. G prime of x times dx is dv. And then f of x is the u. So what you're going to have to do is look at an integral that is given to you. Dx absolutely has to be part of what your dv equals. On top of that, it's going to be multiplied by a function. Sometimes that function g prime, the only thing it is sometimes is the number 1. Sometimes. But now I'm going to go through an example with you and walk you through using this formula. And this is the typical pattern that people use. You'll see what I mean as I start writing this out. By the way, I changed the textbook's example 1 because I want you to see a slightly harder problem and know how to work with it. So what you're going to do when you start off is you're going to write the u and the dv, and you're going to figure out what those two are. Remember that those are the integral you're starting with. When all things come into place, the function you actually end up integrating is going to be v times du. V is the result of integrating something within your beginning integral. Du is the result of differentiating the rest of what is in your initial integral. There's certain types of problems that tend to show up. This is what is often called a type 1. A type 1 is when you have a polynomial multiplied by a sine or a cosine, or an exponential function. When that happens, I want you to think for a moment. Whether I integrate or differentiate sine 3x, I'm going to get a constant multiple times cosine 3x. So whether I put sine 3x in the u or the dv, I'm going to get almost the same thing in the du as I get for the v. So that's not a big deal. But what's the difference with x? If x is the u, I take its derivative and get a constant. If I decide to put x in the dv, right, if I integrate it, I make things more complicated, and then after I have made things more complicated, I then want to integrate something more complicated? No. So when you see a polynomial multiplied by sine or multiplied by cosine or an exponential, let the polynomial be the u, and it will work out beautifully. The dx has to go with the dv, and sine 3x is going to go with it in this case. Now, side note, what you're not going to write down after a while, but I'm going to write it just to make sure that you're following me. You are finding du dx, that is 1, but then you're multiplying the differential over to the other side. So basically you're looking at this and going derivative is 1 times dx. Now over here, what you're not necessarily going to write down, but I'm going to show you blatantly what's going on so you don't get lost. You want to reach the point where you look at this and you know exactly what the answer is with barely doing a u substitution in your head. So watch the u substitution. I'm integrating sine of 3x. I'm making a u substitution of 3x. And yes, that's too many u's used in one problem, but oh well, live with it. And then I need to divide the 3 over to the other side. And this is now the integral of sine u times 1/3 du. Then when I integrate sine u, I get negative cosine u, and I put the u back in. And now I'm ready to write my answer here. What you want to be able to do in the near future, or now, is recognize if you're going to do 3x for your u, you're going to get an extra 1/3. Other than that, what's the integral of sine? Negative cosine, make sure that the u is in there. So you want to become fast, and that's a good question. I'm going to answer that in a second. You want to be able to do u substitutions very quickly when they are just a number times the variable. Otherwise, you can see how much excess work you're going to have to do while you're in the middle of a complicated integral. Now, as far as the plus c, the good news is you're not going to worry about that until the very, 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 very end of the problem because, and I have tested it out to see whether it was true or not, if you put plus c in right now, know that whatever work ends up being done, this is only going to be absorbed within the unknown constant that we're going to need in the end anyway. Because realize we are creating an integral that we are going to then be integrating and getting its plus c. So this plus c will be absorbed into this integral's plus c. But the algebra is painstakingly long. Do yourself a favor and don't put that plus c at that moment. Now we're going to use the formula. The formula says that the integral of x times sine 3x dx is equal to u times v with, I'm taking this out before I start writing it, u times v, which is negative 1/3. I like to put my constants in front. Negative 1/3 x and then cosine 3x, u times v, minus the integral of v du, which are these two results on the bottom. Du is only providing a dx, so I have negative 1/3 constant multiple, and that constant multiple can be brought outside the integral, and it's a negative 1/3. So I'm going to do this. I'm going to go boop, bada boop, and you aren't there any longer. And now you need to integrate cosine 3x. And if you're not quick at your u subs, that's another integral that you have to solve while you're in the middle of a bigger process, and you want to avoid that. So I'm going to do this one the quick way. I have what was already found from the formula. I have my constant multiple times. When I integrate with the u substitution of 3x, I'm going to get an extra 1 divided by its derivative. Then the integral of cosine is positive sine of that u. All integration is done. You may now put plus c. And that's it. You just solved your first integration by parts. It's kind of fun. So I'm going to present you with the forms. These are the forms. I plan to post some notes up during period 4. I'm going to put things together and put up some notes and maybe some annotated notes on top of that. You just did a type 1. A type 1 is where you have some polynomial multiplied by either a sine x or a cosine x or an exponential function. Typically, though, it's e to the x. We're probably not going to have time for the type 3 today. The type 3 is extra fun advanced stuff that the AP test would never do because it is way too time consuming. But you need to see it at some point. We just might not get there today. I don't have that type in the homework for today. But I want to point out to you type 2 before we get there. If you see an inverse transcendental. Now, transcendental functions are the functions that, quote, transcend algebra. Algebra involves polynomials and roots and fractions. So exponential functions are transcendental. What is the inverse of an exponential function? And you're probably about to type it, a logarithm. Then we have trig. Trig is transcendental. And we don't have a fancy name. We just say inverse trig. So these two inverse transcendental functions that you are familiar with, if they show up in an integral, my recommendation is first see if a u substitution, a basic u substitution from first semester calculus, will take care of it, where it is the u in a u sub. If that isn't enough, then make that the u in the dvu process of integration by parts. Everything else is going to be part of the dv. And that's a rule you can follow. Now, before we, oh, that's right, that was my next example. Do you remember that we do not actually have any integration formulas for logarithms and inverse trig functions? That's because you're not supposed to memorize them. You're supposed to know how to come up with them once you learn about integration by parts. So, woo, here we go. As we set up integration by parts, the typical setup is you write u equals, you write dv equals, and you split up that integral. The dx must always go with the dv. Then, if you have a logarithm, that needs to be the u. Everything that is not the logarithm is the dv, and this is a case where we're actually working with 1 being that derivative function, 1 times dx. Now, you know the derivative formula for a logarithm. Now, if you are integrating 1 with respect to x, what do you get? You get x. And I'm going to point out what's going on the side in case you don't see that. If I throw an integral sign onto this equation, if you look at this, you are getting v plus unknown constant equals x plus unknown constant, so only need to write it once. But we're going to ignore the unknown constant at this point because it will be absorbed in the unknown constant in the very end. Showing you, though, that that's true is a mess of algebra. And I don't mean a mess. I mean a mess of algebra. So once we have figured out the derivative and the integral, then we're ready to say the integral of natural log x dx is equal to u times v minus the integral of v du. And just keep in mind that the v and the du are your results of taking the derivative and taking the integral of your two chosen parts. Oh, look at that. That's just the integral of du. What's the integral of... Oh, I'm sorry. I wrote du. Silly me. 1 over x dx times x. There we go. What is the integral of just plain dx? Just x. And now you can add your plus c. So if you're ever wanting a formula for the integral of the natural log, that is the formula. However, in a mathematical setting, you're expected to understand how to create the solution from scratch. Ooh, math is kind of like a snobby cooking class where they're like, oh my gosh, you don't like buy store-bought ingredients. You make stuff from scratch. Ugh, the horror. Yeah, pretty much like that. Okay, the next example, I changed it from... I changed the textbook example so that you could have a slightly more difficult problem so you can handle the homework problem better. Now, I want you to notice which of the two types this is. You have a polynomial multiply... Come on, pen, don't do this to me again. My pen's been annoying lately. It won't respond until I start clicking my mouse on something else and then continue to say, hello, hello, I'm using my pen. There, finally it came back. And I don't know if you could tell that I was sitting there pounding on the screen with my pen until it finally reacted. Sorry, that was my complaint of internet frustration. Here we go. I have a polynomial multiplied by an exponential. Anytime you have a polynomial multiplied by either an exponential or a sine or a cosine, let u be the polynomial. Now, we need to differentiate and we need to integrate. Now, can you do this u substitution in your head? If u is t divided by 5, du is going to be 1/5 dt, and you will take that 1/5 and multiply it to the other side to get 5 times e to the u du. And then you integrate your exponential to get e to the u and pop that u back in. I know not all of you followed that, so I'm going to take this to the side and make sure that you see it, but I'm going to do it quickly. And then right when I would be putting a plus C, I just don't if I'm in the middle of this process. Now I am ready to solve that the integral of t squared times e to the t over 5 dt. And by the way, has anyone gotten to the point where you're angry at me for this problem yet? You have to know. You have to know and understand. And by the way, your dog is adorable. Make sure you're doing the math. So the integral is u times v. So that means I'm going to have 5 times e to the t over 5 times the t squared minus the integral of v du. Multiplying these two together, I am getting 10t times e to the t over 5 dt. And do you see what happened? This process brought your polynomial down 1 degree. That means when you run into a polynomial multiplied by either an exponential or a sine or a cosine, the number of times you must use this process is the same as the degree of that polynomial. So, for the sake of you seeing that this is the way to go through, we're going to do the process yet again. What I'm going to do, though, is I'm going to start by writing out how far I have before I don't write it out. I'm going to take my constant multiple out of the situation as well. And now I'm going to make a side note where I focus on the integral of t e to the t over 5. I need a u, I need a dv. U is the polynomial, dv is the exponential. The derivative of t is 1, so du equals dt. When I integrate, I get an extra times 5. And we just took a look at that. So this integral is equal to its u times v minus the integral of its v du and I'm bringing that back over here, and I love the fact that I can lasso and just bring it over. So pretty. I'm going to lasso this and take it over as well. Okay. We're almost done with this problem. Distributing through, I am getting negative 50 t, and then I'm getting plus negative 10 times negative 5 is going to be plus 50. And then I'm going to solve the integral of e to the t over 5 dt, which we already saw is, due to u substitution, 5 times e to the t over 5 plus c. Woo! Yeah. The good news is I will never give you a process this long on a test. You just need to understand that this is what you have to do to get through it. You could leave the 10t. Wait, where?
It's like for having the so instead of like distributing the 10 outside of the integral, and you just have 10t. So I found it. I did the same. I got the same answer, but that way I didn't have to distribute and kind of almost forget about it.
Exactly. Yes, that's just a personal preference. some people like to, and I found it true, some people like to bring the constant in with this, and some people like to just throw as much to the side as they can, but you still have to distribute. So it's a matter of whether you're okay with that. Yeah, either way is fine. Okay, now, definite integral. With a definite integral, what I do is I actually ignore that it's a definite integral, do the entire process, and then take the full result, the f of x times g of x minus whatever result I got from the integral. And right at the moment where I would throw a plus c on the end, I take the whole thing and do a plug in the b minus plug in the a. And if you look at the way this formula is written, that's exactly what it's saying.
Miss Blanchard,
yes.
I, you know, I think we're 3 minutes over.
Shoot. Okay, what that means is you can go to your next class and I'll keep recording. And if you can stay a little bit longer, you can watch this being done. The class is over at, period 4 starts at 12:55. So you don't have to be in your fourth period until 12:55. If you don't want to go back and have to watch the recording later, but this is in your textbook, it is example 5 if you want to see it from there. Anytime you have an inverse transcendental, let that be your u. The dx has to go with the dv and there's nothing else left. You have to remember all of your derivative formulas. And I'll post those derivative formulas for you. So derivative of inverse tangent, hopefully you remember it's 1 over x squared plus 1, or 1 plus x squared if you prefer. And then the integral so if I stick to the indefinite integral, this is equal to u times v minus the integral of v times du. Multiplying those together, I end up with something that magically says, you sub me, I can do it, I can do it. And while we just had u, I'm still going to use u for my u sub. U gets overly used. So, doing my little u substitution, I can replace my x times dx with 1/2 du. And now it is the integral of 1 over u times 1/2 du, which is then 1/2 natural log of absolute u, and u was x squared plus 1, so I don't actually need those absolute values. You have to know your unit circle trig in order to finish this. Understand on the AP test, you must know your unit circle trig. So now I'm coming back to this point. I've got x times inverse tangent x minus u times v, or no, wait, sorry, I already did that. 1/2 natural log u plug back in. I would throw plus c on, but it's a definite integral, so now I'm just going to take the whole shebang and bring the definite part back. It was 0 to 1. Plugging in 1, I have 1 times inverse tangent of 1. You need to know without a calculator what the inverse tangent of 1 is. When I plug in 0, I'm going to get 0 minus 1/2 natural log of 1, which natural log of 1 is 0. So what you're thinking about is If 1 is the answer to tangent, what was the angle? However, you also have to keep in mind that inverse tangent is only allowed to come up with angles that are negative pi over 2 to positive pi over 2. Tangent is equal to 1 when sine and cosine are equal, which happens when you're at your 45-degree angle. So pi over 4. And then that's the whole problem. Woohoo! My next example was, just in case we had time, we could do the super fun thing that I didn't put in your homework. But we are certainly out of time, so move to your 4th period before you're late.
Thank you.
Uh-huh.